Well, good afternoon. This is 2:32, 2 minutes late getting started, on Monday, the 11th of February, 2019. It's supposed to be Applied Differential Equations class, Math 238. And right now, I'm the only one in the room, so I hope some of the others will be coming in soon. But I'll go on and get started because we're already a couple minutes late getting started. But before I do, I just wanted to make this announcement so everybody can hear. But I'll wait until the students get in here, and then I'll make the announcement. And then everybody will be able to hear from there. So we're going to go from current slide here. And where we left off last time, we had finished 2.1 and all of its various sections, I think 2.1.1 and 2.1.2. And now we're finally in separable equations, okay? We are actually going to start solving some differential equations. Up to now, it's been understanding, seeing how they work, thinking through how they think, that kind of stuff. Finally, we're going to solve some differential equations. Before, they've been saying, this is a solution, this is a possible solution. Now we're going to solve them, okay? So the simplest of all these are the separable differential equations. If you have separable differential equations, go for them, enjoy them. They're the easiest usually to do. And what we say, we solve by integration. However, it's sometimes not quite that simple, but it comes down to that. And there will be other ways we can solve too, rather than this way. You'll hit that, as we get later in this chapter and into other chapters. But here's what we mean by solution by integration. Okay? Let's just say we have a function. Let me get my pen set up. Okay. Consider a first-order differential equation, ordinary differential equation, dy dx is equal to some g of x. In other words, there is no y dependence on the right-hand side. All it is left-hand side. Now, this is almost a stark contrast with what we're doing at the end of section 2.1.2 when we were looking at autonomous differential equations, and those were ones that the right-hand side was strictly a function of y with no x dependency. Okay? So now we're doing the opposite of that, where it's strictly a function of x. Okay? Now, if g is an integrable function, now if it's not, it's going to be hard to find a differential equation, an equation that's going to solve that differential equation. But if g is integrable, okay, then this is typically how they do it, okay? A pure mathematician would say, write this in differential form. And that would be this. dy is equal to g of x dx. Okay? And then we'd say integrate both sides. Okay? Well, the integral of y would be, dy would be y. And integral of this would be whatever like I said, if g is an integrable equation, this is what you would do. Okay? You would integrate that, and that would be some function of x, let's call it capital G of x, plus c, okay? And that would be our solution, okay? If g of x was integrable, then if its antiderivative is capital G of x, then that would be our solution, with c being your parameter, okay? If g of x is a continuous function, then integrating both sides, and that's exactly what I got, okay? Blah, 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 okay? Now, what if we had something a little more complicated like this? dy dx is equal to, not more complicated, but it's fleshed out a little bit more, 1 plus e to the 2x. Okay? Well, the thing on the right is only a function of x, no y's over there at all, so we write it in differential form. And that would be dy is equal to 1 plus e to the 2x dx, and integrate both sides, and this would be y is equal to, antiderivative of 1, of course, is x. Antiderivative of e to the 2x would be e to the 2x, 1/2 e to the 2x. And then you'd have a plus c, okay, which again would be your parameter, single parameter. All right. Now, take a derivative of this and see if that's what you get. dy dx would then be 1 plus e to the 2x times 2, which 1/2 e to the 2x times 2 would be e to the 2x. So yes, then your initial differential equation is fulfilled. Okay? And that would be your general solution. Okay. So here is the definition that goes generally in this way. Now, they're going to make a leap here. Okay? This was all saying if your equation on the right-hand side is strictly a function of x. The next is going to be if the equation on the right is some f of xy. It has both x and y dependency, but, okay, if this f of xy can be factored into a g of x times a h of y, then we can do the same thing we just did. The only difference is we will do, after we write it in differential form, then we'll divide by h of y, okay? And then you would have your dy over h of y, okay? Now, and that's equal to gx dx. Now we said that g had to be integrable. Now 1 over h of y has to be integrable, okay? And that may be a little bit tougher to find, but a lot of times it will be something we can handle, okay? So with that in mind, let's give the definition, okay? Pretty straightforward, hopefully simple definition, and here's what it is. Definition 2.2.1, separable equation. A first-order linear differential equation of the form, so first order DE, differential equation of the form, and this is dy dx is equal to some separable function of x and y, g of x times h of y. If you can separate, factor the right-hand side into an x dependence and a y dependence, that is said to be separable, or to have separable variables, okay? So it's called separable, or have separable variables. Usually we just shorten to say it's a separable form, okay? Now, here are a couple of little examples. dy dx is equal to y squared x e to the 3x plus 4y, okay? Now, stop there. That doesn't quite look separable. Sure, the y squared can be separated from the x squared, factored out, but that e term has both of them in it. Until you remember what a principle of exponentials is, okay? write down the y squared x, just like before. This can be written as e to the 3x times e to the 4y. Because when you multiply same base, different exponents, keep the base, add the exponents, and that would get you right back to this form. Ha! Now we can separate. Get the y terms together and the x terms together. Okay? And then you could rewrite this as dy over the y terms, y squared e to the 4y, is equal to x e to the 3x dx. You write it in differential form, dy on one side, dx on the other. Divide out all the y's to be with the y's and the x's to go with the x's, and here you have it. Now, remember, part of what I said, though, is if this is integrable. Now, that's yet another story here. First thing I would try to do is write this as y to the minus 2 e to the minus 4y dy. And then, investigate some way, and it looks like integration by parts might work. And in this case, though, I think I would be going with let u equal your e function, which is backwards of what we usually do, and the du being y to the minus 2 dy. And the reason for that, the next integration is going to take you to e minus 1, and then one more in that direction will take you to a log y, and then you're going to wind up with e to the y's and log y's, and you might be able to work it out. Or you might be able to find it in a table somewhere, or keep reducing it until you get to a form that you can use a table, okay? They're all not going to be easy, okay? So those separable equations are the easiest differential equations to solve. You still got to have ways to solve the integrals that come out of that. And this one doesn't look like a particularly, the right-hand side, piece of cake. That is integration by parts. Once and you got it done. The left-hand side, however, could be a lot hairier. Okay, so that's one example of a separable equation. Whether it's easy to integrate, that's another issue, but it is easy to separate. Okay, now the next one is this one. dy dx, this looks a lot simpler, doesn't it, is equal to y plus sine x. Guess what with this one? You cannot separate that into a product. It's a sum, but not a product. And there's no way any kind of manipulation you can do will get that to be a product. It's always going to be a sum. So this is not a separable equation. Now, there are other techniques we're going to hit in just a few sections that will allow us to solve that one, but not separable. Not separable. Not the easiest one. Okay? So of these two examples, the first is separable, the second is not separable. The first equation, you can factor that, and just like we did, second equation, no way of expressing that as a product of function of x times a function of y. Okay? Now, it says, observe that by dividing the function h of y, we can write the separable equation dy dx is equal to, I think we've already done that. What we were up here saying would then be, if I said it, I already erased it, dy over h of y is equal to g of x dx. You write it in differential form, getting your dy dx is our opposite side, leave the x one with the x and divide by the y. Now what they say to do is then rewrite this 1 over h of y as p of y. Now, I really don't like that notation, because when I see p of y, I think polynomial of y, and this is no guarantee that that's going to be a polynomial of y. So why they did that, I'm not absolutely sure, but they're just trying to get it into something a little simpler. From the last form, you can immediately see that 2 reduces to 1 when h of y is equal to 1, so yeah, no sweat there. Now, if y is equal to phi of x, represents a solution to this form here. We must have a p of phi of x, phi prime of x equal g of x, and therefore basically all they're saying, this thing, if that's integrable and you could come up with a function h of y, and this is integrable, now that's pretty clearly that could be a g of x, then they're only going to differ by some constant. Okay? Which is the same thing we said before, why it took them so long to get down there, why they have to introduce a phi and a phi prime and all that kind of stuff. I don't know, it just makes it more complicated. Okay. All right. They just basically are blah, blah, blahing for ways. And they say, note, there's no need to use two constants of integration. Combine them both into one, usually on the right-hand side. There's no reason to write a separate one for each integral, okay? Because not necessary, okay? Just one constant will do for both, okay? So let's actually do one, finally. Example 1. We've talked all about them. Let's do one. Here's one. Solve 1 plus x dy minus y dx is equal to 0. Now, that's not real clear what kind this is, except that you see it is separable. You might call this a homogeneous equation because it's equal to 0, okay? It's already in somewhat of a differential form. I'd say just a differential form. What you can do is get your dy's on one side, and that's 1 plus x dy by adding y dx to both sides is equal to y dx. And now divide both sides by y, but also divide by 1 plus x, because you want your 1 plus x's over here with the x, and you want your y's over there with the y's. So here those goes out, these go out, and you have a dy over y is equal to dx over 1 plus x. Now if you integrate both sides, this, I hope by now you recognize that as being natural log of y. Need to put absolute value bars unless you're, for some reason, a priori, you know for certain that y can never be negative, then you wouldn't need absolute value bars. But if you don't know that, always assume it's absolute value. And over here, you have almost the same thing, the log of absolute value 1 plus x. Now, if you knew always that x was going to be something greater than -1. Notice I didn't say greater than or equal to -1, greater than -1, okay? X couldn't be a sine or cosine function because occasionally it's equal to -1 and you can't take the log of 0. So you have to have x being something greater than -1, never equal to, greater than -1 for all values of x, and well, for all values, and then you could remove your absolute value bars. But without that, you can't. You need them in absolute value bars, unless you know that. Okay? And then what we don't have is our constant, so just put plus C. Okay. Now that's one way to write your C. What you could do, perhaps, is write this C as a log C, which would be okay, wouldn't it? That's still a constant, and we'll assume C is positive. Then, what you could do, since these are two like this, you could write this as log absolute value y is equal to the sum of two logs is the log of their products, right? The log of C times absolute value 1 plus x. Okay? Now that's the same deal, right? Because the log of a product is the sum of the logs. Okay? Now you've incorporated the C into the function, so to speak. Now you can take an E of both sides, and that gives you absolute value of y is equal to E to the C times 1 plus x. Now, here we can lose the absolute value signs. I think you can legitimately do so, because E is never negative. Okay? E is always greater than or equal to 0, never even equal to 0. Okay? So now you can do that. And that's another way to express your there he is. Well, if I were on the right page, that would be helpful. There. Nope. One more page over. I looked down and saw 237 and thought it was 238. Here we go. Let me fill out the top here. Today's the 11th, 12th, 13th, and 14th. Need to know this. Thursday's Valentine's Day. That's important.
Oh, I've been reminded. Don't worry.
Okay. We got you here. Glad you're here. It's a lot better to talk to someone than to talk to myself.
Yeah, you're not a big fan of that, are you?
Yeah. So I'm going to turn this on and then put my lights. Or turn on some lights. It gets more dark because it's kind of gloomy outside.
Yeah, it is. Well, it was started to sprinkling too.
Did it? Okay, I saw Dr. Bryant come in with some pretty heavy looking stuff on, so I thought things must be a changing a little bit. And this is mid-February and we're already got trees budding. That just seems early. What's that?
That means we're going to have a cold snap.
I'm afraid so, and that could be a bit on the hazardous side then. Okay, we're in section 2.2, which is separable equations, and we're example 1, bottom of page 48, and it's going to move on to the top of 49, and I was just expressing this in a few different forms that it could take on. I didn't quite follow the same way the book did. And I see now where I made a tactical error. I said we take the log of both, the exponential of both sides, and I wrote exponential and didn't write the log of C1 plus x. Now, I'm not doing it quite the same way the book did, but the exponential of a log would be, exponential of a log is just what's inside. It would be y is equal to c times 1 plus x. Now, I've got a bunch of extra lines in there that are not necessary. Okay. Now, the book, and I don't know, oh, they finally get to that. Yeah, this is their final answer. They went about it a bit more strangely. They left the c there rather than making this constant a log c, which is still a constant. And making a log c, I thought, made it work out. So this is a solution, a fairly simple looking solution for that relatively simple looking differential equation until you got into it, and you wound up with logs on both sides and stuff, but then by judiciously adjusting those to be this, that is your solution. Purely a series of linear equations, different c's of course are going to give it different values, including slopes and everything else, and y-intercepts as well. But that will be a solution. C is your parameter for your one. So one parameter solution. Okay, I guess it's the easiest place to say. Y is equal to c times 1 plus x. And by doing it this way, because it's introducing the logs, exponential function, exponential always positive, so you can lose the absolute values, and then you just have c is equal to 1 plus x. So it's, again, not totally clear that's all legal to do, because if you put a proper x in there, -3, then that makes y negative, but then from back here you say y can never be negative because you took a log of it. So it doesn't quite look like the domain is quite fixed, but it doesn't seem to raise any problem with them whatsoever. Okay, and I don't know why. Okay. Now, that's our first separable differential equation, and you see it came out a fairly simple solution. Now, one thing I don't like about the way this looks, it's not a very curved parentheses. Curve it a little bit more than that. Okay, that's the answer they get. Okay, any question? Okay, that leads then to example 2. This time they give you an initial value problem, IVP, and here's what you got: dy dx is equal to negative x over y, when knowing that y of 4 is equal to -3. There's your initial value. Now, initial doesn't mean when the independent variable is equal to 0. Sometimes we think of it that way, especially if it's time, you think that's initial. It doesn't have to be time. In fact, it's x. It's a displacement. That's where you start. So that's where it would be. Would x equal 4, y is equal to -3. Okay. Now, where would you begin? Okay, now that's one way of doing it. Pure mathematicians would cringe at that statement and they'd say, write it in differential form. But that's exactly what it looks like you're doing. dy is equal to minus x over y dx. Okay? Now, you don't quite have your variables separated, though, so what could you do?
Are they completing the square?
What's that?
Are they completing a square?
No, what you're trying to do is separate the variables. Here you have a y by itself, that's defined in the form of dy, but over here you have x with a dx, but you also have a y with the dx. You don't want that. You want to separate them. So what we're going to do, multiply both sides by y. And that will wipe out the y over here, and now you'll have a y dy is equal to minus x dx. Now you could have dragged the minus sign across there too if you wanted to, but there's not any real reason to do that. So now let's integrate both sides. And what do we get? Y squared over 2 started to put dy, you don't need dy anymore, is equal to
negative x squared over
2 plus c. Now they didn't give us any, oh yes we did, they gave us our initial condition. So let's plug and chug there. Just for funsies, let's just multiply everything on both sides by 2, and that gives you y squared is equal to minus x squared plus, instead of 2c, we'll just make it c. I mean, c is a constant, 2c is also a constant, so let's just let that be our constant. Okay? Now,
how'd you get rid of the denominator?
I multiply both sides by 2. And multiply this by 2, but 2 times c is still a constant. Right. Okay. Now we'll plug in our, what we know. We have that y is negative 3, and negative 3 squared would be 9, is equal to negative, x is 4, so x squared would be 16, plus c, so c is equal to 25, right? Okay, so now we write down y squared is equal to minus x squared plus 25. Well, what is that? If we put our x squared over here, added x squared to both sides, we'd have x squared plus y squared is equal to 25. That basically defines a circle of radius 5. Okay, that would be the solution. Now, trouble is it's not a function, so it's either going to be the top half of the circle or the bottom half of the circle. One or the other. So I guess the better way, sorry, to have written this is y is equal to plus or minus square root of 25 minus x squared. Okay. Going back and subtracting that x squared again. So depending on which, oh, and we know that y is negative when x is positive, so this is going to be the minus. No question. Not plus or minus, because when y is equal, x is equal to 4, y has got to be negative 3, so that means we choose the bottom half of the circle.
Well, say that again. When x is, oh, you said 4.
When x is 4, y has to be negative 3.
Right.
So when x is 4, we're down here at negative 3. So therefore, we're the bottom half of the circle, not the top half. Top half is now out of there. It's the bottom half of that circle from our initial condition. Okay. If that initial condition, say when y of 5 would be 0, then we don't know which one we're on. It could be either one, or y of negative 5 is equal to 0. That we could be on top half or bottom half, but we can't be on both. Okay. Now the family of curves would be all the concentric circles around here, not just with integral radii, but with any fractional radii as well. We just happen to be, with this being one possibility, that another, this another, that another. Well, this is the one we happen to be on. The one of radius 5, the bottom half. Okay, from our initial condition. All right. Now, have a little warning blurb here. Some care should be exercised in separating variables since the variable divisors could be 0 at a point. Specifically, if r is a 0 of a function, h of y, then substituting y is equal to r into dy dx is equal to g of x h of y makes both sides equal to 0. In other words, y equal r is a constant solution of the differential equation. Okay, but after variables have been separated, the left-hand side separated from the right-hand side is undefined at r, and as a consequence, y is equal to r not show up as a family of solution obtained, blah, blah, blah. Recall such a solution is called a singular solution. So you might possibly lose a singular solution through separation of variables. So you sort of just have to keep it in the back of your head. Are there any others that don't fit this but could still be solutions? Like the trivial solution 0, 0. Okay. Now, let's go to, this will be an example of that, I think. Here's what we've got. dy dx is equal to y squared minus 4. How would you go about solving that?
Divide by dx.
What's that?
Divide by dx.
Yeah, or multiply.
Yes,
Yeah, okay. All right, so that would be dy is equal to y squared minus 4 dx. Okay, otherwise that's written in differential form. Now, the variables aren't separated, though. What would you do to separate them?
You have to subtract y squared.
Yeah.
Y squared is negative 4.
Yeah, 4. Okay. I'm having trouble writing, I don't know why. These go away then, so you have dy over y squared minus 4 is equal to dx. I can do the right-hand side. The left-hand side might take a little more work. Okay? Right-hand side is just going to be x. And you could have a plus, depending on which side you want your plus c to be, going to put it with the x plus c. But the left-hand side, don't know if you remember this from probably Cal 2, partial fractions. Okay. When you have a polynomial in your denominator of an integral, and your denominator is a greater degree than your numerator. Here your numerator is 1, so yeah, y squared is larger degree than y to the 0, which is 1. Then you factor your denominators into linear factors if you can. If you can't, irreducible quadratic factors. Well, this will factor. This will factor very nicely as into what?
Y plus 2, y negative 2.
Exactly. Okay. Now, a little bit of review on what we're doing here. Our integrand, what's inside there that we're trying to integrate, is 1 over y plus 2 times y minus 2. And here's what the methods of partial fraction says. Split that denominator into one fraction that is, say, a over y plus 2 plus b over y minus 2. Okay? Because if you think back when you were doing fractions, which was a lovely time, and you had, say, x over 6 is equal to something over 3 times something over 2. Yeah, whatever is there, you could split it into a half and a third. When you add, find least common denominator, it's going to be 6, and then you work it out. That's exactly what we're doing here. We're just doing it in reverse. We know what the common denominator is, split it into 2 pieces, and then, this was the trick, multiply both sides by this denominator, y plus 2 times y minus 1, because we don't, y minus 2, okay? Because we don't like denominators, do we? No. Okay, so we'll multiply this by, by y plus 2 times y minus 2, multiply this one by y plus 2 times y minus 2. As long as you do the same thing to both sides and every term to both sides, it's legal, right? Well, here, obviously, both of those go away. So you're left with 1 on the left. Goodness, this drives me nuts. Here, the y plus 2's go away, and you're left with a times y plus 2. Oh, y minus 2, sorry. And here, the y minus 2's go away, and that leaves you with a b times y plus 2. Okay? Now, you got to figure out what your a and b's are. Okay? There's a couple of ways. The easy way, which I'm all in favor of, is pick a y. Now, this doesn't seem fair, but neither do some of the other things seem fair either. It works. Choose a y equal to, say, 2. Y is equal to 2. What we have here is Muhammad present. Okay? All because y was 2. Okay? That did it for us. Okay. Now, and we'll even go back for you. What we're doing is example, which one?
2.
2, on page 49. Yeah, nope. We're down to example 3. Example 3. Bottom of 49. Okay? Now, we're going to choose a y. Like, oh, I wrote it down. Y is equal to 2. Well, 1 is still 1. Okay? No matter what y is, 1 is still 1. Is equal, but when y is equal to 2 here, that goes to 0. And when y is equal to 2, then this would be b times 2. So b is equal to 1/2. All right?
B times 2.
Second?
How did you get b times 2?
Because y is equal to 0. I'm sorry. 4. B, okay. 1 is equal to, y is equal to 2. 2 plus 2 is 4. Yeah. Second? The first one goes to 0. When y is equal to 2, this goes to 0, and this goes to 4. So then you have 1 is equal to b times 4, and divide by 4. So b is equal to 1/4. Rather ugly, but true. Okay? Okay. B is equal to 1/4. Okay. Well, that works so nicely. Let's do the same thing again, but let's this time say y is equal to -2. Then you have, go back to the top, you have 1 is equal to a times -4 plus b times 0. Hey, that would be a is equal to -1/4. Okay? So, go back to your left-hand side here, and you have the first of these things. Instead of this as your integral, we're going to do this one, but we're going to put -1/4 here and +1/4 there. So I'm going to reverse the order and say that this integral here is the same as the pair of integrals, the integral of 1/4 times dy over y minus 2 plus 1 minus 1/4. Sorry about that. I reversed the order and I forgot to stay with my reversed order. Okay. Minus 1/4 times the integral of dy over y plus 2. No. B is 1/4. That would be the plus. This is the minus. Sorry about that. I keep reversing so many things. I can't tell which way I'm heading. Okay. I think that's it. Okay. So that's your left-hand side. Your right-hand side is merely x plus c. So this is 1/4 times the natural log of y plus 2 minus 1/4 times the natural log of y minus 2 is equal to x plus c. Okay. Now, the rest is manipulation. Okay. What you could do is factor out a 1/4. Let me, since we've already used this, I hope we use it correctly. Let's get rid of all this, our scratch work here that came up with the a equal 1/4. No, I had that right. Yeah, that's right. Okay. I think I have it right. And b is equal to minus 1/4. No, the b is equal to 1/4. So I had it backwards then. I thought I had it right the first time. That was my I've already erased it, so I can't tell for sure, but I believe that was my minus and that was my plus. Okay, so it makes that the minus and that's the plus. Okay. So minus here, plus there, minus there, plus there. Okay. Now, get back to my erasing again. It's not erasing. All right. What's that? That's what?
That's also one way of erasing.
Yeah. If you're going to erase, it must erase. Okay. This is just going to give us some more room to work if I can ever get these things to erase. All right. I hope we got those right. Let me just do a sneak and look in the book and make sure I did. Positive, yeah. Yeah. Yes. Got it. Now they call it C1 and then keep changing the numbers. But let's do the next step, which is factor out the 1/4. And that would then be the log of absolute value y minus 2 minus the log of absolute value y plus 2 is equal to x plus c. They can call it C1 or anything you want to. What you could do is multiply both sides by 4 if that really floated your boat. So let's make this a 4x here and get rid of that. Okay. Now, the sum of two logs is the log of the quotient. Remember? One of the log rules. The log of a quotient is the difference of their logs. Yeah, it's one of the, let's see if those are found anywhere in here. rules. I don't know if they have them in this book or not. They're in a lot of books, but I don't know if they have them in this one. Let's see. Oh no, that's Laplace transforms. I have a feeling they're not in here, but let's just look and see. It would be right before the index. If I can get my pages to turn. Those are your appendices, your chapters, Laplace transforms, matrices. Wow. Integral defined functions. I don't think we want that. And that looks like we're out of luck. Okay. Just a little bit of review on logs. I'll erase this in a minute. The log of AB is log of A plus log of B. I don't know, do y'all remember that? I know this dates me really bad. Do any of you even know what a slide rule is? Oh, you do? Fantastic. Okay. Remember how you can multiply numbers, not to exact precision, but to like 2 or 3 decimal places with a slide rule. And what you did, the slide rule was ruled in log scale. So you took one number, say 17, you multiply it by 243, you find 17 on the log scale here, put your 0 for the slide there, and then add to it the log of 243 here, and there's your answer, and take the anti-log of that, and there's your answer. That's what a slide rule did. It added logs to do multiplication. It subtracted logs to do division. So that is indeed, if that's multiplication, then the log of A over B would be log of A minus log of B. So that's why I said this could be written as a division. So I'm going to erase that if it's all right. Is it? Okay.
All right, go ahead.
Okay. So this, if I could get it to erase, there it goes. Okay. Would be log of y minus 2 over y plus 2. We could put the absolute value around both of them is equal to 4x. And I didn't multiply by c because 4 times c is just another constant, so let's leave that as a constant. Now, then I could take the e of both sides, okay, and that would give me y minus 2 over y plus 2, because you take the e of a log, you lose both of those, is equal to e to the 4x. And you could do plus c, or make it e to the c, and make that just some other constant. C, or k, or c1, or c2, but it's just a constant, okay? Get out of there. Okay. It's just some constant. So we'll just say c. Bigger c, little c, whatever you want to call it. Okay. Now, that's probably still not the form they have it in. Okay. And it's not plus, it's c times that. So I'm going to take that c and write it in front. That's a better place for it, actually, than messing with all that. Okay. Now, that gives you 2 y's in one place the x is, which is a little awkward too. So what they do here, and it's kind of magic, let's multiply both sides by the denominator, because we don't like the denominator, right? Okay, so multiply this by y plus 2. Okay, and that's going to wipe out that one, because it's y plus 2 here. Okay, and they're both gone. So now you have a y minus 2 is equal to c e to the 4x times y plus c e to the 2c to the 4x, right? Okay. I multiply both sides by y plus 2, and then this multiplied by that, and this multiplied by that. Sort of separate those. And then let's add 2 to both sides. I hope I'm going the same direction they are. Two plus, oh man.
Why not keep it factored?
Second?
Why not keep it as a factored factored equation, like, c, e to the x times y plus 2. Why not leave it factored like that?
Okay, I'm sorry, one more time.
Why not leave it factored?
Leave the factor.
Why did you go ahead and distribute the C, E?
Right. Well, I'm beginning to think that may have been a really bad choice of things to do. Because actually, I need to go back a few steps to do it. They took a slightly different bent here. They have exactly what I have here, there, okay. And then they do the E here, this quotient thing here. So let's erase this, okay. And they have that form. I'll even take off that, okay. Now, here's where I have a little bit of a problem seeing what they're doing. Okay, I'm going to take off this too. I'm going to expand this a little bit. The y of this, and here's what I'm having trouble seeing right now. They introduce a plus or minus e to the 4x plus c, keeping that the same way. They're doing an e here, but why did they say plus or minus? And I am not quite sure why they did that. Trying to see where that plus or minus came from. You do the e of both sides. Why does it come up plus or minus? Oh, I think. This step still had the absolute value on it, okay? So now you don't need the plus or minus. No, I'm sorry. This step still had that, okay? So to go from this step, okay, it's a little tricky. To lose the absolute value bars, that means this is either plus or minus. So to take off the absolute value bars, I'm going to take them off this way. That should have been there anyway. If you take off these, that's when you have to put the plus or minus in. Because it's either plus or it's minus. You know, you can't. If the absolute value of this is that, then lose the absolute value, it's either going to be plus this or it's going to be minus that. You know, we just don't know whether it's plus or minus, but this allows you to be either. Okay. This is then where they, okay. Same thing I did, but this is where you multiply by y plus 2. Okay. All right, and I know your question now. Here you multiply by y plus 2, and here we multiply by y plus 2. All right. Now, that leaves a y minus 2 here is equal to and this is I don't know why they hung on to this so long. You could take this e to the 4x and e to the c, and e to the c is just a constant, so they bring it down here. But now it's a plus or minus here. Up here they were doing C1 or C2 or something, because e to the 4x plus c is the same as e to the 4x times e to the c. It's just, yeah. And e to the c is just a constant. So let's make that our new c, okay? You could have subscripts for each one. It's just a constant, so we can make it a c. So that's where I had already done this. They hung on to it until now. Okay, so I had made this a c here, but I had forgotten the plus or minus sign. So when you add 2 to it, then you lose this and you get 2 plus or minus c e to the 4x okay, which you could then write y is equal to 2 plus c e to the 4x, or y is equal to 2 minus c e to the 4x. Okay. But then you multiply this by x plus, and here he is. Peyton's here.
Sorry.
All right. We're still missing Justin and Terrell and Jordan. Okay. Half of you are here. That's good. All right. Okay. But we still have it. Yeah, okay. Thought I had the wrong pen in my hand. We haven't multiplied by that. Okay? And that's what your question was. Why don't leave it in factored form? Because they don't, okay, is one answer. If you had multiplied by this, and I know that'll come back in a minute, but I'm just trying to get it to do. This would be get it the way I want to say it. Whew. See, they skip a bunch of steps that I really don't care for skipping. And it's hard to justify why they did, but here's what you get. Y times c e to the 4x. I think you have to have a plus or minus in there, but we'll come back to this. Plus 2c e to the 4x. Okay? that's when you multiply that through. I know your question was, why do it? Well, because they did it. Okay, so that's where this term came from. Now, we still got a plus or minus in there. And then when you add 2 to it, you have 2 plus or minus e to the, and I'm afraid I'm going to be erasing things I need, but I just need the room. So, okay. I guess we're through with this down here. So let me go on and erase this. Yeah, we are. I'm sorry. That's a problem with recording with this. I'm stuck on a small screen. If I was working on the board, I could take as much board as I want, but then it wouldn't be recorded. So in order to record it, I'm stuck with this small screen, and I can't get everything on here. Okay. Okay. All right. So what we have is y is equal to 2 plus ce to the 4x plus 2ce to the 4. Wait. This one has a y in it. That one has a 2 in it. Or 2 minus y c e to the 4x, and let's see, I believe that will be a minus 2c e to the 4x. Okay. Now, here's where the magic comes. If you move this to the other side, so you have y, and I'm going to change this to plus or minus yce to the 4x. These two terms, either plus or minus, move them to the other side. One becomes minus, the other becomes plus. And that's equal to 2 plus or minus ce, 2ce to the 4x, because you move these two and you've got those two left. Okay? Now, factor out the y here, and you have 1 plus or minus ce to the 4x. Factor out the 2 here, and you get 1 plus or minus 2ce to the 4x. Yuck. Okay. Now, divide both sides by this, 1 plus or minus ce to the 4x, 1 plus or minus ce to the 4x. Okay, and that's how they get to, and I was pretty sloppy with this. Sorry. When you or subtract, or when you're moving this to the other side, that becomes a minus. Moving this to the other side, it becomes a plus. So I should have done minus or plus here, and then, so this will be minus or plus. This is plus or minus here, to make them match up. Well, it doesn't matter. One's a plus and one's a minus, so it doesn't matter which. So that's why here they leave this, when these go out, here's what their answer is. Y is equal to 2 times 1, and it really doesn't matter which you put where. I guess they put the plus on top. Plus ce to the 4x over 1 minus ce to the 4x. Now, the reason is your 2's factored out on this side, and you left, and I left the 2 in there, I shouldn't have. You factored it out. So that's why you have the same thing over itself, only one's positive and one negative. And does it really matter which is which? I'm not absolutely sure. I guess it probably does. And I can't for the I guess you should just hang on to one of them. When you hang on to one, that puts the other there. But they don't do the plus or minuses anymore, but that's where they wound up. Okay? And that, to me, is no cleaner of a form than what we had at the very beginning. I was just trying to show you how they got to this form. And except for the plus or minus deal and minus plus deal, that's what it winds up being. Let's see if this would help any. This would always have the larger number on top and the smaller number on bottom, I think. And that's exactly what you want. You want this to be a fraction greater than 1 rather than a fraction less than 1. Because you don't want that ever to be the y to be, where was it? Basically, the y always has to be greater than or equal. In between minus 2 and 2, okay? Because, you see, it can't be 3. 3 squared minus 4. And that, I don't think is allowed. Because we took a log of it at some point, and you just couldn't have that happen. Okay, I know that's a really lousy description, but that's how they came up with that form. Our form is just as good. There's no real thing. Only thing is it's an explicit solution of y in terms of y, rather than having y's on both in your logarithms and other places too. Those are really pains in the neck to carry through, as you just saw. And that is y is an explicit function of x. Okay. You do all that, and if we factor the right-hand side, you know the discussion of critical points has you, now what they're doing is going back up here, just factoring here rather than waiting down here and saying y plus 2 times y minus 2. Now we're back to our autonomous form, where everything on the right is all y's. There's no x's there, okay? Well, now you know you have a critical point at minus 2 and one at plus 2. So you could have two separate set of equations. This one, I don't think that allows that, because you only have one y for any given x, whereas up here you have 2. You could be up here or you could be down here. Two different functions, one place or the other. This, pick an x, any x, and it's just one value. You don't have the upstairs and the downstairs. And that's why they said you basically have lost a solution, okay? So why did they take you through all that if we could have just done it in that form? Well, they're saying separation of variables may not be the best way to go, especially if you have an autonomous solution like this. Then you have to do your figuring on two different domains. I mean, one domain, two different ranges. Are you down here or are you up here? And you lost that when you went through and did it that way. And where did you lose it? Why did you lose it? Probably taking out the absolute value signs. I can't say that's for sure where it happened, but my guess is that had something to do with it. Okay. Now, if you had an initial value problem, you would have wound up in the right place. because your initial value puts you either down here or up there, and you don't even see the other solution. So that's what we're going to do next, as long as there's time, and there's no time. We just went over. So next time we'll begin with example 4. Okay. Homework exercises here. We almost got through with 2.2. You can do any of the odds that are in the back of the book anyway, 1 through 21. I think most of them are back there. I think that you can do any of the odds 23 to 27 if they're in the back. And stop there. We'll pick up the rest of those next time. All right. Good deal. I hate that kind of problem there because there's so many, oh, but if or when, you know, and especially in the book, they just say, and this goes to this, you know, with not a hint of what's in between. But that's how you got to those forms. How they drop the signs, I've not figured that one out yet. But supposedly it does hold water, or else they wouldn't have put it there.
Do you have a class? You don't have a class.
No, I'm free now. Did want to say this. I'm going to do it before I shut this down. I don't know if any of you are interested ever in teaching math. I don't know for certain that's what this is about, but the Noyce scholarships, Alabama A&M has just recently got a grant to do these. We're a partner with them, so we can send our students up there. It's a summer program. They pay you to go and participate. They feed you, they house you, they give you transportation, pay your transportation once coming and going. Alabama A&M is near Huntsville. It's actually in what they call Normal, Alabama, I think, which is somewhere just outside of Huntsville. I don't know exactly where, but it's almost in Huntsville.
What's the name of it?
Normal, Alabama. I think it's on A&M, yeah. Isn't it on the north side of it?
Probably right on the Tennessee border.
Okay, it could be. I'm guessing it used to be a teacher school because they called those normal schools. So, and it may actually be incorporated in Huntsville. I don't know. But anyway, it's a good program. But if you want to find out more about it, check your email because you got this just like I did. And you can check your Lawson State email and find out about it. You may find it's a pretty neat program. We've had students go to it at Alabama and UAB when they had them, but they're only 2 to 3, 4, 5-year grants, something like that. Theirs probably are on the way out. This one's just getting started. So if you're interested, check your email. It has a link you can go to.
If you're proceeding for a degree, that would be a great.
Not just math or any science.
Oh,
Physics.
any science?
Yeah, any science. I think maybe you'll have to check and see, but it's math and science. At Alabama, it was math, chemistry, and physics. They didn't include biology because they just had enough graduates in biology.
Engineering is a biology, or is a bachelor's of science?
Yes, and well, I don't know if it's Bachelor of Science, but I mean, I know engineering is, but if you could wind up teaching either math, chemistry, or physics. That was the one at Alabama. You'll have to see the details here at A&M. So, if you're interested.
That's crazy.
What's that?
That is kind of crazy. Any science I would have expected. Yeah, a targeted program like math, I can understand. Yeah. That's very broad.
Yeah. Well, the chemistry or physics, what the deal is, especially in Alabama, but just all over the country, there's just such a shortage of science and math teachers. I mean, extreme shortage. Yeah, huh?
I'm noticing.
Yeah. And so they're just...
Especially a shortage of excellent ones. I mean,
yeah.
To be honest, I've had... There was one really good math professor at UAH. And you're probably the best math professor, at least I know of in Birmingham.
Yeah.
So it's so hard to find good math professors.
I'm talking K-12, you know, math and science teachers there. Yeah.
Because you got to have almost all of the knowledge of either an engineer or a math doctorate to even teach high school math.
Yeah.
And they can use most of it.
And what winds up happening so many times I've heard of, anyone who's hired in the school system, this is especially elementary, the newest kid on the block is assigned to teach math because no one else wants to teach it.
Yeah.
So the teacher who probably got into elementary ed because she didn't like math then winds up having to teach that her first time when she has the least experience teaching and maintaining class and managing a class and all like this. She's ducked on teaching her least favorite subject. Now, not always the case, but quite often it would be. And that just, you start off then teaching kids to be scared of math.
Same thing with the yearbook at Shades Valley. It was always or even any school I know of, the newest teacher that gets dumped on them too.
Yeah, yeah.
It's a big responsibility that they place new teachers to organize these things.
All right. So if you're interested in looking into it, or if you know anyone who is, point them that direction.